So, example problems on Gauss theorem, electric flux and electric field. The question says, an insulating sphere. Don't just read and think maybe your business is fair. Always pay attention to, is it conducting sphere or insulating sphere? Or is it insulating or anything or conducting anything? So an insulating sphere of radius 3.5 meter contains minus 60 microcoulomb of electric charge, uniformly distributed throughout the volume of the sphere. A. What is the electric field 2 meter away from the center of the sphere? Let's draw this sphere. You know the goal. You know that my goal for every class is make sure you are not cramming. Make sure you understand it because it's physics, physically. So if this is an insulating sphere, let's say you draw this thing, you use your compass and draw this with radius of 3.5. So let's say this is the radius 3.5 or 3.5. So let's say this is 3.5. Then if this is an insulator, I taught you something. So let me come and draw this thing now. So if this is an insulator, I told you that charges, unlike a conductor that we have its charges, just one or two outside, or just on the like edges to attract going outside. This one, the reason it's an insulator is because it has charges packed that does not move. Insulator is when something can move, when the charges can move, that is when it's a conductor. So the charges are packed. The things it has that make it up are packed. It's an atom. Everything is made up of atom, if you remember, are packed. So if this be the case, so let's say from here to here, we know that it's 3.5, then they are now asking us electric field 2 meter away. So anytime you want to calculate from the center, 2 meter away from the center, I wish you can really pay attention to the voice I'm using, the thing I'm saying, not you waiting to get to the point you want to pay attention to. Listen to what I'm saying. 2 meter away. Remember that the radius from this end to this end is 3.5 meter. That means 2 meter away is still inside here. So let's say I want to get the electric field to be on this axis. This axis. Electric field can go here, go here. Once there's charge, there's electric field. It's just that when it's an insulator, it will be slow. Remember electric field intensity, which is electric field. I told you they are the same, just that different terms used in describing it. So electric field intensity talks about how strong the degree of strength that the charge use in moving. Is it too fast? The direction, is it too fast or too slow, or how? So if an insulator is weak but there's electric field, any charge, once there's presence of charge, there's electric field intensity, electric field. So this end to this end should be 3.5. Let's say from this end now to this end is 2.02 meter away from the center, which cannot happen if it's a conductor. If it's a conductor, it can only be on the outside. So any part you are looking for electric field, the collection of electric fields, which can be up, down, different areas, different directions, is what we call, or where we employ Gaussian theorem, which says that which says that electric flux, which normally is, that's where we employ electric flux, which says that electric field on a surface is equals to the total charge enclosed in the system. So let's say we enclose from this end to this end, this 2 meter. Let's say we enclose it. So I'm using a sphere too. Since it's a sphere, I'm using a sphere. So I'm enclosing the charges. So those charges that fall in between from center to 2 meter, from center to 2 meter, I've enclosed it. Now that I've enclosed it, I can now say, okay, let me now find this. And notice everything they talked about here. Remember I told you, whenever you're talking about charge distribution, electric field distribution, always pay attention to what you are given. Notice that from the question, they did not say throughout the surface. They said throughout the volume of the sphere. Distributed throughout the volume of the sphere. So what I'm using this time around is what we call volume charge density, or charge volume density. That is what I'm using. Volume charge density. So that is why I'm not using area. And volume charge density is the same thing I told you, rho equals to density is mass over volume. So but I told you always in electricity or electric field, always take charge as mass. So Q all over then volume. You see it? So that if I make Q subject of the formula, this can go on and attract volume charge density times volume. So if I know this, I will now go back to my understanding. I need you to understand that once it's volume we are dealing with, if it's volume you are dealing with, from here, this place that you are seeing this thing now, from here, you need to pay attention to the volume of this Gaussian surface and the volume of the sphere. Note it is a formula that you must note. So the PV I'm using should be PV of Gaussian surface all over V of sphere. So this of Gaussian surface and that of the sphere. That is how you put it. And you know that this will be Q equals to P. Volume of a sphere is simply 4 over 3 pi r cube. Yes. That is the volume of a sphere. Yes, volume of a sphere. That is why I told you that if you differentiate volume, you get area. For example, if I do 3 times 4 is 12. Then minus 1 from 3 is 2. So 12 divided by 3 is 4. You get 4 pi r square, which is for area, but this is for volume we're dealing with. So all over, if you like, go and be paying attention to example and illustration I'm making on differentiation. If you don't know differentiation, forget it. This is what we're doing. So notice that for Gaussian surface, I will call this R here. In this case, this is the bigger R. The R from this end to this. So let's say this is the R. Why the R of the Gaussian surface, I want to use it as small r. So I will now say that of the surface will be 4 over 3 pi r cube. This way. I'm using R for big R. Are you not seeing that the radius from this end to the surface is bigger? This one to this one is smaller. Let the charge not confuse you. See what I mean? This is what radius is. So for Gaussian surface that we establish, anywhere you want to look for electric flux, always establish an enclosed system. If you pay attention to the definitions I gave you earlier when we started class. So this is what I've done. So you can see that it's now easy for me to come and remember I said this is a constant, it's a rule that must be obeyed. The volume you are using, you take cognizance of the volume of the sphere and that of the Gaussian surface. So if I do this, I'll see that if you put this thing together now, you will see that it's easy for you to say, let's say I do this thing like this, Q equals to P 4 over 3 pi r cube divided by 4 over 3. Oh God, what am I doing? Let me give space. Q equals to P 4 over 3 pi r cube divided by 4 over 3 pi r cube. You know, if it is standing on is over 1. Using reciprocal law, you see that this is the sentence I'm saying Q P 4 over 3 pi r cube times 1 over 4 over 3 pi r cube. Everything here will cancel this. This will cancel this. So I'm left with Q equals to density. Remember that this P, I'm not doing it well, but it's supposed to be going up. Rho. Call it rho for density, volume density. Charge, yes, volume charge density. So R that I'm seeing here, all over R3. So this is for our charge here. So if I've noted it, I will go back to why we always do this. This is an understanding you must have. So I've been able to derive charge from the volume density. Assuming it's area they told us we use it, but here they told us above volume. I'm able to derive charge here. I will now go back to the Gaussian, apply Gaussian theorem, which is EA, electric flux, is equals to Q, charge enclosed all over permittivity of free space. So replace, so replace, I have EA. Okay, let me put my E. That is what I'm looking for. Then this is a sphere. Area of a sphere is 4 pi r square. That's the area of a sphere. then equals to charge. I have uh yes, I have P, yes, R cube all over R3. Yes. So if I make E subject of the formula, yes, and remember that there's epsilon 0 here. So I got, this is Q, everything about Q. So divided by E naught. So over 1. So this is the same thing as saying P R cube over R cube times 1 over E naught. So I now have E into 4 pi R square. And you know that to make E subject of formula is the same thing as saying divide by 4 pi R square. So that this becomes E equals to P R cube all over 4 pi. Okay, notice something. Before I carry on so that I don't disturb myself, this R square, since it's small r, remember that this R square, this is area of surface, Gaussian surface, if you remember. So okay, yes, wait. Yes, wait. Yes, see, that time we started. This is, yes, area of Gaussian surface. Then this one, the area that is always here is that of the charge. So, but they did not give us area here. So this is area of Gaussian surface, yes. So I now have R square cancel one of these, two of these. So I now have, yes, now area of the surface, which I said is Gaussian surface. Go back and watch my video. So I now have, this has cancelled, and now, so this is not supposed to be here. What I'm supposed to have is just one R remaining on this. So I now have epsilon 0 here, then I have my R cube. So if you remember very well, E will now be equals to, if you remember very well, you remember that 1 over 4 pi epsilon 0 is K. So E will now be K, KP, yes, KP, because yes, now see, KP. So it's just like, let me check it. I have 1 over 4 pi epsilon 0 to be equals to K. So if it becomes K, so PR, then all over R3. So anytime, it's simple. You do it yourself. If you don't understand, do it, pay attention, rewatch it, pay attention, do it, you see it. So anytime you are giving charge or volume charge density, or you are giving volume, you are now asked to find area or have no connection with area. What you are told is about volume, you use charge volume density or volume charge density. When you arrive that your E will be this way. And you remember that K has a formula. This is where the thing might confuse you, how we put this thing out, but remember, there's 1 up here. 1 times PR is 1. So see it. So you now have, so if you know this, to find E now, 2 meter away from the center. 2 meter away from the center. Let's check something. Yes, 2 meter away from the center. So remember that will be this R. 2 meter away from the center will now be K. E will now be equals to, K is 9 times 10 raised to power 9. Yes. 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 No, yes, raised to power 9. Then P, did they give me volume density? Let's check if they gave me volume density. So before I'm thinking of using this, because notice that I have this now as the formula. So let me check if they gave me volume density in the question. There's so much air here, turning my paper up and down. Did they give me in this question, did they give me volume density? They did not give me volume. They did not give me volume. So since they did not give me volume, I have to remember. I have to go back and remember something. I need to remember that this charge volume density is equals to this. Equals to Q over V. So let me replace this. So let me go back. I'll go back and see. Let me replace it. So I have K. So I remember that E will now be equals to K, then Q over V times R divided by R3. So K Q R over V times 1 over R3. So this is what I will use. Why I'm using this is because I know that charge volume density is Q over V. So I don't have it given to me. So I will now plug in to find E equals to. So K is 9 times 10. Yes. So even, yes, okay, let's go on. So raised to power 9, yes. Then charge that I'm giving away from the center. So I'm told that the charge here, I'm told that contains minus 60 microcoulomb electric charge uniformly distributed throughout the volume of the sphere. So if I'm getting this 2 meter away, I'll use that charge. So I'll use that charge. It's an electron. That's the one I'm using. I'll use an electron, that charge. So assume, and whatever you get, the only thing is that you have a negative answer. But if they ask you if it's proton, it's going to be positive one, because you know that charge of proton and that of electron is the same thing. So I'll now put, but notice that 1 million microcoulomb is equals to 1 coulomb. Is it not? Coulomb. So that means that uh 60 microcoulomb, in as much as is minus, will be equals to x coulomb, cross multiply, so that I now have minus 60 coulomb is equals to 1 million microcoulomb times coulomb. Yes, and this one is microcoulomb, then times 1 coulomb. So that this will cancel this. Then I have x coulomb. This will cancel this, don't worry. But x, I don't know x, and x that I'm talking about is x coulomb, so no need cancelling it. So divide, and anything times 1 is that. So divide both sides by coefficient of x, which is 1 million. So it's the same thing as saying 60 divided by 1 million. So it's the same thing as saying 6 times 10 raised to the power minus 6. 1, 2, 3, 4. Yes, children? Yes. So it's the same thing as saying, yes. So it's the same thing as saying 6 times 10 raised to the power minus 5. Sorry. But, no. So if I know that, so times 6 times 10 raised to the power minus 5. So times 1, anything times 1. Okay, yes, times r, sorry. R, and the r I'm giving 2 meter away. The r is the small r for the Gaussian surface. So 2 all over V. Is it not V we are running from? Volume. Did they give us anything about volume? Let's check. Let's check. Since we did Q over volume. Okay, yes, volume. Volume of the sphere. Volume of the sphere is volume of sphere is given by pi 4. Oh yes, pi should be 4 over 3. 4 over 3 pi. Yes. Then, and since the sphere is the big square, so pi r cube. But since we are dealing with a way, and this is, yes, volume of charge. So I'm using volume of charge. Charge. Okay, the volume we are supposed to use for the charge, that is for this charge, supposed to be that of the smaller, the enclosure. So r cube. So times our big R. Our big R is 3.5. 3.5. And remember that this one is 2. So it's going to be E equals to Let me do the punching. Okay, so lest we forget, remember that the column given to us is electron. So I've put it minus. So by the time you times it, everything will give you minus 180,000. Yes, that is 1,080,000. Yes, so all over 4 over 3 times 22 over 7 times 2. Yes, then times 3.5. 3.5. So if I know this, I will now have let's do the maths. I'm coming back. Okay, so you will now have E equals to minus 1080,000 all over 29.3333. You know, I've told you I like using 4 decimal places. So E will simply be equals to, let's divide now. I have 10. You know, I'm being too fast. Please punch your own. Punch your own so that you'll be sure that I'm not making a mistake, like I've not missed any number. I'm trying to be fast and avoid the air. There's so much air here and I'm enjoying it, but I don't want to off it. You know, I'm making a video for my students, people that come for classes, and I need to read. So if you're an international student watching this, if you have any question, please refer to the comments. I will make video specifically because of you. So divided by 29.3333. And when you punch it, you now get E equals to, notice that it is minus because of the minus charge given to us. So it will be minus 36.818.22. So yes, so this is, yes, 818.22. So 36,818.22. So and electric field intensity is given by shebi, let's think about it. E equals to kq over r square. So you have coulombs up here all over meter square. Then you remember that K on its own is equals to Newton shebi meter square per coulomb square, if I'm not mistaken. So let's put everything together. So if I put Newton meter square per coulomb square, so you see that you have this cancelling this, cancelling this, cancelling. So you have Newton yes, coulombs. Newton, yes, because if this is down, if this happens to be down, so let's do it this way. So I don't have it off. So when you do it well, you see that it will give you Newton per coulomb. I even forgot, stressing myself, I forgot that E should be equals to also force per unit charge, if you remember, which is Newton per coulomb. So when you know it, you know it. However you go about it, you'll be able to get it. So Newton per coulomb. So you know that charge is coulomb. Electric current is ampere. So know it. So if I know this, this is my final answer. So it's an electron. So this is my final answer. So there you have it. You might have that issue of maybe saying this one should be R, the big R. But remember, we are talking about volume here. And the volume we should be considering, since we've enclosed that electric field and we're talking about 2 meters from it, should be the volume of the sphere. That is the enclosed, that is the Gaussian surface. So this is my answer. So let's move to the next question. So the B part of the question said, what is the volume charge density? volume charge density. Remember that we said that volume charge density is given by P equals to charge, that is rho, charge over, that is mass over volume, so charge over volume. And we notice that the volume, sorry, yes, okay, so let's do it. So I'll say rho B part should be equals to charge. So where you see, I told you in electricity, treat charge as mass. So all those places you normally see mass, normally put charge there all over volume. So to find this will be equals to, the charge given to us is minus 60 microcoulomb. And this is the same thing as this saying, so we got it to be 6 times minus 6 times 10 raised to power minus 5. So all over, the volume will be 4 over 3 pi 4 over 3 pi r cube. You know true, it's true. 4 over 3 pi r cube. So and the r we are using here in this case, notice they did not tell us anything about, they are considering what they've given us when they ask us for B. A is a part of this question that is on its own. We found that one. If we want to find volume charge density for 2 meter away, 2 meter away, we can now put arrow there to be 2. But remember that they gave us insulating sphere of radius 3.5 meter. So the radius I'm going to use when I'm calculating volume charge density of this insulating sphere is that of 3.5. So I will now do this equals to minus 6 times 10 raised to power minus 5 all over 4 over 3 times 22 over 7 times, so I'm going to be using r cube, not, so r, which is 3.5 raised to power 3. So I just hope that all the places we solved earlier, shit man, shit, did I remember to put this? Shit, look at this, when we did this one, that has q, that is ks, qs, then we have rs, then when we did this one that has 4 over 3, then r raised to power 3, this is supposed to be 2 raised to power 3. This thing that we have here supposed to be 2 raised to power 3 because it's our r, then times this. Shit man. So let's do it so that we have 4 and 2 raised to power 3 is 8. So I know that I always, whenever I'm rushing like this, I always have something I forget. 2 over 3 times 22 divided by 7 times 8 times 3.5 equals to, should be 117. Should be 117.3333. So let's do 1080,000 divided by 117.3333. So we have, wow. So what we actually have, E is actually 9,204.55 Newton per coulomb. So thank God about that. So let's go back to business. So for this one we should be having, we do this way, we should be having, let's do the denominator first. 4 divided by 3 times 22 divided by 7. Yes, so we know that 3.5. First of all, Yes, I'm getting 10.5. Sorry, no, 3.5 raised to power 3. What are you doing? I said 10.5. Are you okay? So 42,875. So I have 4 divided by 3 times 22 over 7. So let's now do 6 times 10. I know the sign will be there because it's a negative charge. So 6 times 10 raised to power minus 5 divided by 179,666.67. I'm not use my phone as well as well. Okay. So this is going to be 3.3395 times 10. Remember, it's having minus. Times 10 raised to power minus 10. So please make sure you do this calculation. Drop your answer too after solving. I know we are correct, but I just feel I'm being too fast. So minus 3.34 times 10 raised to power minus 10. And surface charge density, since it's charge over volume, so it's going to be coulombs per meter cube. So there you have it. So now for my answer is negative because we are using negative charge. Most times you see positive answer is because you are using proton. That positive value that they give you means it's proton. So they now said what is the electric field? Question says, what is the electric field 4.2 meter? What is the electric field 4.2 meter away from the center of the sphere? What is the electric field 4.2 meter away from the center of the sphere? Let's do it. So electric field 4.2 meter away from the sphere is simply going to be, let's draw. I have the insulator. Now it has charges. It's not moving, so all the charges are just packed. Now it's no longer when I have enclosure. So since they said, notice that this total, the radius from here to here is actually 3.5, 3.5. So if they now tell me 4.2, it means that they want me to go outside. So if I measure this thing now from here, it will extend outside to give me like 4.2. From here to here should be like 4.2. That means I will get my Gaussian surface on the outside, which is the regular surface that normally happen with conductors. So if I get this now, this is the 4.2. So this becomes big R, this becomes small r. I'm using it this way. So if you know this, what I will simply do now is to employ the same approach. Whenever I have volume density, the only thing I will just need to do is to do this thing I did again, all over. Are you seeing it? So volume of the Gaussian surface and this one. So the only thing that will change is you knowing that you need to know that that of the Gaussian surface will always be up, and that of the sphere will always be down. Yes. So at the end of the day, you now have this like KPR all over R cube. So I feel I will allow you do this one. Solve it for me. So solve this one as classwork for me. In our next class, we'll do it. So put your answer on the comment section. Thank you.